Greetings everyone. Welcome to this session on Introduction to Construction Stage Analysis. I am Anuj Asati. I am a Senior Structural Engineer at MIDAS IT. In this session, we are going to look at the importance of construction stage analysis in bridges. So whoever wants to learn about construction stage analysis or wants to know how to perform construction stage analysis in MIDAS Civil, this session will be useful for them. This session will be of around 45 minutes, and post that we will have 15 minutes of question answer session. So if you have any questions during the session, you can post them in the question answer section and we will try to answer them at the end of the section. Okay, so let's start with this session. A little bit about me. So I am Anuj Asati. I have been working in bridge engineering field for past 5 years. And before joining MIDAS, I worked as a design engineer for L&T. So here I was part of a design team that worked on DFCC railway project. So DFCC is dedicated freight corridor that is built in India. Now in MIDAS, I am part of a European team where we provide technical support to engineers and help them solve their problems. So now let's move on to our today's session. So let's first look at what are the things that we are going to cover in this session. So first we are going to look what is construction stage analysis and why is construction stage analysis needed. So here we will try to answer the questions like construction stage analysis is needed or not for our bridge. Then we will look at certain considerations that are needed to be taken in construction stage analysis. Then we are going to move to time dependent material properties. Here we will look at creep, shrinkage and compressive strength. Then we will move on to pre-stress loading, construction stage analysis in MIDAS Civil. So here we are going to understand this with an example of 3-span continuous bridge. Once we cover all this, then we will move on to the question answer session. So now I hope you all are ready for the session. So let's start the session now. Now let's first answer what is construction stage analysis. So as you know, there are various construction methods to construct a bridge. For example, balanced cantilever method or incremental launching method. And these construction methods involve various steps of construction of the bridge. For example, suppose I am constructing a bridge with balanced cantilever methodology. So first I will construct the piers of my bridge. Then I will launch the segments one by one, and then at the end I will launch the key segment which will be joining the left and the right segment. Okay, so as you can see, there are various steps involved in this construction method. So when we model each and every step of this construction in the software and we analyze each and every step, that is called the construction stage analysis. Now that we have answered what is construction stage analysis, we also need to ask the question, is construction stage analysis is needed or not? So to answer this question, we need to look at certain conditions. For example, we need to answer if is our construction statically determinate or is it indeterminate? Okay, so for a statically determinate bridge structure, we generally perform the analysis taking the final configuration of the bridge and applying a number of different loads that are coming on the bridge. And then we investigate the moments and shear forces and find the critical forces on our bridge, and then we design the bridge. Okay, so however, when we go for a statically indeterminate bridge structure where continuous deck is built in number of different stages, things can get a bit complex. Sometimes a change of a system during the construction can result into a more critical condition for structure compared to that of the final state. For example, if I am constructing a cable stayed bridge as shown in the image, an intermediate step can be can give more critical forces on my pylon as compared to the final state. Hence, for such kind of special structures, we need to take into account the moments and forces that are coming in intermediate steps as well, so that our structure is safe through construction as well as post construction. Okay, then second, so we have discussed if it is statically or statically indeterminate, then change in the bridge configuration as well. So as I have told you, suppose however my bridge has been constructed, an intermediate configuration can be more critical. Then coming to multiple span cast in situ continuous concrete bridges, which are often built span by span with cantilevers at the end, which we are going to see in our example as well. Span by span construction involves a staged construction using shorter tendons that overlap at a certain distance near the pier. So this approach yields in saving in false work as well as in form work. In continuous bridges erected using span by span method, the stress can be significantly different than those that are cast in full length at once. So don't you think the design should consider the changing structural configuration as construction progresses along with the long-term results as well? Along with long-term behavior as well. So now that we have established what is construction stage analysis and should it be needed or not, now let's move on to various effects that we need to consider in construction stage analysis. Now, to understand the importance of construction stage analysis, these two models are created. And after analysis, their bending moment distribution results are compared. So in first method or model, we didn't consider any construction stage analysis. The whole three-span continuous bridge, the loading was applied and then moments were calculated, moments were found out. However, in method 2, a construction sequence, the actual construction sequence of bridge was modeled. So in first stage, the first span was launched, then the second span was activated, and in stage 3 the third span was activated. Now let's see how the results were for both the methods. We can see here the value of sagging and hogging moment when no construction stage analysis is performed. Here only static analysis is performed. So you can see here we are getting a hogging of 180 kilonewton meter and sagging of 120.4 kilonewton meter. Okay, now let's look at the results with construction stage analysis and let's compare both the results. Here we can see the values of sagging and hogging moment when construction stage analysis is performed, considering the sequence of construction. Here we can see there is a significant change in bending moment distribution. So here the sagging moment is dominant as compared to the hogging moment. So you can see the distribution is different. So here we are getting a sagging of around 145 kilonewton meter as compared to 120 kilonewton meter sagging in previous case, and here we are getting a hogging of 120 kilonewton meter. So you can see there is a significant difference. Hence we need to incorporate the construction sequence into our analysis, so that whatever forces that we are using are accurate for our analysis. Now that we have established the use of construction stage analysis, let's look at various considerations that we need to take for construction stage analysis. So let's discuss some important considerations that should be taken into account while performing construction stage analysis. And MIDAS Civil has capabilities to consider the following. And construction stage analysis is needed for statically indeterminate bridge structures, and the different considerations that we need to make are: one, the time dependent material properties. So here we need to consider creep in concrete member as then we need to consider shrinkage, compressive strength, and relaxation of a pre-stressing tendon. And suppose if we are having a composite section, in that case, we might the creep maturities will be different for both the section, which will result for both parts of the section, which will result in differential creep. Similarly, we will have differential shrinkage as well. In addition to this, as the construction steps are different, so activation of each member will be different. Hence, they will also have different creep maturities and shrinkage maturities. That's why it is important to consider creep and shrinkage for construction stage analysis. Then compressive strength, as you know, the strength increases with time, and the concrete achieves FCK in 28 days. So that's why we need to take into account that effect as well. Then conditions for construction stages. Now, you know, the activation or deactivation of members with certain maturities need to be taken into account, as well as the loading when the loading are activated, so that need to be considered. So suppose load is activated at 0th day of construction and activated at 20th day of construction. Both will be different cases, as the strength of concrete will be different at both the both the steps. Similarly for boundary condition as well. So suppose during construction the boundary condition is changing. So for example, we are doing a full cast in situ construction. So in that case, the deck will be completely supported till 28 days, and after that the false work will be removed. So these types of construction, these types of boundary condition will change during construction, and that need to be taken into account. So we can consider all these material properties, as well as we can simulate all the construction conditions of construction stages in MIDAS that we are going to look at in the example. Okay, so now let's look these time dependent effects in detail. Now let's look at the time-dependent material properties. So first look at creep. So you are all aware of creep. So as you know, as the time passes, volume of concrete changes that results in creep and shrinkage. Okay, and these changes in concrete create stress, cracks, and deflections, thus affecting the serviceability of the structure. And a creep in concrete, as you know, is defined as deformation of structure under sustained loading. So when a constant load is applied to concrete, initial instantaneous deformation occur. So that you can see in the image, initial instantaneous deformation, which is the elastic strain, occurs. And even though there is no additional load applied, creep increases the deformation over the time, which is called as creep strain. And you can see the change in creep strain is also not constant. Creep deformations occurs quickly in the beginning, but the rate increases this rate gradually decreases over time. And suppose if that load is removed, so elastic recovery happens. You can see the elastic recovery when the in the load removal, and then the permanent deformation. There is certain permanent deformation remains. So when the load is removed, there will be a elastic recovery, as well as there will be a creep recovery, but there will be a permanent deformation that will remain due to creep. And there are various factors that affect creep as well. So a few of them are like age of the concrete, which is under load, then the sustained stress, the level of sustained stress, relative humidity, temperature, size of structure, and water cement ratio. So this is how these are the factors that affect creep, and this is how creep action occurs in a structure. Now let's look at the codal guidelines on how to consider creep effect in our analysis. Now let's discuss the creep coefficient formulation as per Eurocode. So the creep coefficient at any given point of time can be calculated um, with a notional creep coefficient and development of creep with time after loading. So the notional creep coefficient can be obtained by multiplication of relative humidity, concrete strength, and concrete age at loading. So the phi RH, which is relative humidity, can be calculated as per the given formula. So it is also influenced by the concrete strength, which is reflected by alpha 1 and alpha 2. Similarly, beta FCM, which represents the concrete strength, can be calculated as per the given formula, and beta T naught can also be calculated. Similarly, for development of creep, beta C T naught can be calculated as per the formula shown in the image. Here, beta H represents the relative humidity and notional size of member, which governs the rate of creep in a particular member. So all these formulations are implemented in MIDAS Civil. So with basic inputs like age of concrete, relative humidity, age of concrete at that since from when the creep is considered, as well as relative humidity, notional size of member. If such parameters are given as input, then creep coefficient can be calculated at any given point of time. Okay, so this is how the calculation of creep coefficient is carried out in as per Eurocode in MIDAS Civil. Now let's now let's look at how the creep coefficient graph is calculated in MIDAS. Here we have considered a member of 1 cross 1 meter, and here SCK is 35 MPa. Relative humidity we have considered as 80%, and the time of loading, since when a creep need to be considered, is 3 days, and type of cement is class N, and temperature is 20 degree. And based on the formulation discussed in the previous slide, here we have drawn a graph of creep coefficient with respect to time as per the manual calculation shared in the previous slide. Besides that is the creep coefficient graph with respect to time, which is generated in MIDAS Civil based on these inputs which we have discussed now. And you can see the graph is almost like similar in both the cases. We would also recommend you to try to verify the creep coefficient at once at your end, also once if you are doing if you are taking into account the time dependent material properties. Okay, so you can see the creep coefficient are almost they match exactly as per the manual calculation and as per the calculation prescribed in Eurocode. Now next look at the shrinkage strain calculations. Shrinkage strain at any given point of time is a sum of drying shrinkage strain and autogeneous shrinkage strain. Drying shrinkage strain can be calculated with the help of development of drying shrinkage, basic drying shrinkage, and coefficient, which is dependent on notional size, which governs the rate of shrinkage in a particular member. So the basic drying shrinkage can be calculated as per the formula shown here. So this is dependent on the strength of concrete. Then development of the drying shrinkage can be calculated beta ds as per the formula shared in the image. Similarly, for the autogeneous shrinkage strain, Beta AS can be calculated with as per the formula. So here beta AS is a time dependent formula, and similarly strain CA at time at infinity can be calculated as per the formula shown here. Based on these formulas, the shrinkage strain can be calculated at any given time, at any given point of time, and that need to be used in our analysis model. Now in the next slide we will see how shrinkage strain is calculated in MIDAS Civil as compared to the manual calculations. Shrinkage strain calculation was made for a similar section for which we did the creep coefficient calculation. So 1 cross 1 meter section with FCK as 35 MPa and relative humidity as 80%. And the start of shrinkage is taken from third day, and type of cement is class N, and temperature is 20 degrees centigrade. So for that, the manual calculation of shrinkage strain is shown on the left side of the graph, and on the right side is the shrinkage strain with respect to time graph generated in MIDAS Civil with the same inputs. So you can see the shrinkage strain also matches to with the manual calculations. So like this, at any given point of time, the shrinkage strain will be obtained from the graph and will be applied to the analysis, and based on that, the time dependent effects will be considered in the analysis. Now next let's look at the compressive strength, how the compressive strength variation is considered in MIDAS Civil. Now the compressive strength at any given point of time can be calculated as per the formula shown here. So here we have to give an input of FCK plus delta F, which is nothing but FCM. So here delta F is nothing but a standard deviation of the strength of concrete. So so that input we have to give, and based on that the strength of concrete is calculated with respect to time, and then this strength will be used in the analysis. So at any given point of time of analysis, the strength can be obtained from this curve. Now we have covered creep, shrinkage, and compressive strength. Now we will look at the pre-stress loading in MIDAS Civil. Okay, so now let's look at pre-stress. Now let's discuss about the pre-stress load. So you might know that there are two types in which we can do the pre-stressing. We can go for a post-tensioning, or we can go for pre-tensioning. And based on the type of pre-stressing, we can define the losses basically in two categories. One can be categorized as instantaneous loss, and the other one can be time dependent loss. So when we apply the jacking force, then we will have instantaneous loss. Then the initial jacking force will be reduced to initial pre-stress. Then with time there will be more losses that will be coming in our structure, and with after reduction of those losses we will get the effective pre-stress. So for instantaneous loss we have elastic shortening, friction, and anchorage slip, and for time dependent we have pre-stress relaxation, and then concrete creep and concrete shrinkage. So suppose when we are going for a post tensioning, so at the time of once we apply the jacking stress, there will be immediate loss due to anchorage slip. Then there will be relaxation of steel before transfer. Then there will be elastic shortening that will be happening in the member. So these all will come in instantaneous loss. Then there will be creep, shrinkage, and relaxation. These will come in long-term losses. Okay. Similarly, for for pre-tensioning, we will have elastic shortening that will be happening instantaneously. So this will come in instantaneous loss, and then we will have creep, shrinkage, and relaxation, which will be the time dependent losses, long-term losses. Okay, so next we will look at the live example of a 3-span continuous beam, where we will see how we can model all these effects of creep, shrinkage, compressive strength variation with respect to time, and pre-stressing, and account and see all these losses for our structure. Okay, so now let's move on to the live example, and yeah, so let's move on to the live example now. For our example today, we are considering a 3-span continuous box girder bridge. So the span length of our bridge is 40 meters plus 45 meters plus 40 meters. So the side spans are of 40 meters and the center span is of 45 meters. And the total carriageway width is 8.5 meters, of which 7.5 meters is clear carriageway. So now in the next slide, we will see the construction sequence that we will be adopting for our bridge. Now this is the construction sequence that we are going to follow for our bridge. So we are going for a full staging method. That means it is a cast in situ construction. So in the first step, we will cast the first span of our bridge plus 8 meters of a cantilever. Then in stage 2, the second span, the rest of remaining of the second span will be cast in place, and then part of a third span cantilever. And in the third stage, the remaining part of span 3 will be casted. Okay, so this is our construction sequence that we are going to follow. Now let's move on to our software demonstration part, where we will see how to simulate such construction sequence, plus how to take into account the time dependent effects of creep, shrinkage, compressive strength, and pre-stressing for our analysis. Now let's move on to the live demonstration. Now let me just open the software for you, and let's see the demonstration of construction stage analysis in MIDAS Civil. So now here we are in the software window. So this is our basic GUI of MIDAS Civil. So who all are new to MIDAS, I'll give a brief introduction about the GUI. So what you see at the top here is our main ribbon menu. So all the options for the operations that are performed in MIDAS can be accessed from this ribbon menu. Then here at the left we have this tree menu 1, and on the right is a tree menu 2. So this tree menu is kind of a log where everything what we do in our model is recorded. So be it creation of element, definition of material, definition of section properties, or definition of load, assignment of supports, all of these things can be logged and can be accessed from the tree menu. Okay, so we have two tree menus. So these two tree menus are helpful for accessing two different commands at the same time. Then at the bottom here we have the message window, where all the messages related to analysis, or if there are any warnings or errors, will be reflected in this message window. Then at the center we have our main modeling window, where whatever modeling we are doing will be reflected here. Okay, now this is our structure. So we have drawn the basic structure. Now for this we have to define our construction stage analysis. Okay, so to define the construction stage analysis, the first important step is to define groups. Now in groups we have to define structure groups, boundary groups, and load groups. So the purpose of defining these groups is, with the help of these groups, we will activate a part of structure, boundary or load at any point of time during construction stage, and we can deactivate them also. So basically these groups provide us the tool using which we can activate or deactivate any part of structure, boundary or load group during any part of construction stage. Okay, so now you can see I have already defined these structure groups here. So here if you see this structure group 1, which is CS0, is our substructure. So this I have defined as CS0. That means in the first stage, which is CS0, our substructure will be activated. Then I have CS1, where span 1 and part of cantilever span 2 will be activated. Then in CS2, the remaining part of span 2 and cantilever part of span 3 will be activated. And in CS3, remaining part of span 3 will be activated. Similarly, I have defined four boundary groups. The first boundary group is for substructure. So whatever boundary groups that are associated with the substructure are added to this sub boundary group. That means substructure boundary group. Then this BG1 is the boundary associated with span 1 activation. So if I just turn on these boundary conditions, you will be able to understand them better. Now the end support of my pier will be activated in with substructure, so that's why they are added to sub boundary group. Similarly, the bearing and connection between deck top and deck bottom will be activated with my span 1 structure, so those are added to boundary group 1. Similarly, the links related to span 2 activation are activated in are added to BG2, and similarly for span 3 activation they are added to BG3. Okay, similarly all the loads are added to their respective load group. So here we have defined load groups of self weight, SIDL, pre-stressing. So here for each girder we have provided 8 strands, 4 strands on each web. Okay, and then we are going for a sequential post tensioning where each strand is stressed after one another. So PS1 represent strand PS11, PS12, PS13 and PS14. So if you see here, let me just display the tendon profile first. Okay, so this PS1 represent the first strand in span 1, PS21 represent the first strand in span 2, and PS31 represents the first strand in span 3. Similarly, we have 4 strands, one on each web. So PS1, PS2, PS3 and PS4 similarly. So 4 strands, 2 on so PS1 will represent one strand on one web, and one strand on either of web. So there will be 2 tendons assigned to this PS1. Okay, so if you see here the tendon load also, you will be able to understand that. So let me, so this is the tendon pre-stress load. So here, so A1L left, so that means first strand in left girder, and A1R right is first strand in right girder. Similarly, we have so here A represents the span 1, B represents span 2 and C represents span 3. Okay, so like this we have created the groups. So the reason why we have made different load group for pre-stressing. This is because we will be activating strand 1, strand 2, strand 3 and strand 4 at different point of time in the construction stages. The reason for doing this is to capture the effect of sequential pre-stressing. So that's why we are doing this. So in a moment we will see how we can add them in different points of time in construction stage analysis. Okay, so the first step is to define the structure group, boundary group and load group and assign the specified structures to those structure group, boundaries to boundary group and loads to load group. Okay, now the second step for construction stage analysis is to define the construction stages. So now I will define the construction stages here. So here my first stage is CS0. Okay, so CS0 is created. Similarly, I'll create CS1, CS2, CS3, then CS4. CS4 is a long-term stage, so we will see its definition as well. So the purpose of defining CS4 is to capture the long-term effects of creep, shrinkage and other time-dependent effects on the structure. Okay, so my 5 construction stages are defined. Now let's define the first construction stage. So duration of this stage so let me give you first the what each and every icon here means. So first we give the stage name, then here we have the duration of stage. So that means for how long this stage is going to run. Okay, then we have here element tab, boundary tab and load tab. So here all the element structure groups that we have defined here will be shown here in element tab. In boundary, all the boundary groups that we have defined will be shown here, and in load, all the load groups that we have defined will be shown here. Okay, now if we want to activate any structure group in this stage, we can add them here in the structure in the element tab. Now here we have to give the age of element as well. So this will be the age of element at the time of activation. Suppose I am activating my substructure at the age of 28 days. So here I will give the age as 28 days. So many times users confuse between duration and age. So suppose I am activating CS the substructure at age of 28 and the duration of my stage is 1 day. So the age of my substructure at the end of this stage will be 28 days plus 1 day. So this is how it is easier to remember. Then we have the deactivation tab also. So suppose I want to deactivate a part of my structure. So I will add that structure group here in deactivation tab. So here I have this redistribution option. So whatever forces that were resisted by that structure group will be redistributed among the neighboring elements. Okay, so this was all about the structure group. Then we have the boundary group. Similarly, similar to structure group, we have these boundary group. So here we have option to activate them in original and deformed shape. So as you know, suppose I am constructing a cantilever beam in 3 parts. So when my first part is activated, so that first part will undergo some deformation. So the second part of my cantilever beam will be activated from that deformed shape of first part, right? So if that is the case, in that case we have to use the deformed we have to activate in deformed condition, or else if I want to bring back the deformed shape to original shape of activation and then activate my further elements, in that way I have to go for original boundary condition. To know more about this original deformed, I would recommend to go to online help manual and read about this, how originally deformed shape work. Okay, so here we can activate a particular boundary group, and we can select either it is original and deformed. Similarly, we can deactivate as well a particular boundary group. Okay, so this was about the boundary group. Then we have the load group. So here we can activate or deactivate a particular load group here. Then we have option to activate it at first at the start of the construction stage or at the last step of the construction stage. And not only this, here we can add a particular step as well. We can add more steps here. Okay, suppose I want to add steps at 0.02, 0.04. So these are in day, the unit is in day, so this will be converted. If I want to convert this into hours, so that will be 0.02 into 24. So once I have added these steps, now you can see these steps here. So I can add a particular load intermediate construction stage as well by adding these steps. Okay, so here using this section we can add time steps as well for activation or deactivation of load. Similarly, we can deactivate a load as well at particular stage, at particular duration in a construction stage. Now this was about the 3 tabs. Then we have the option to save results. So we can save result at stage, that will be the end step, or we can save the result at additional steps as well. So additional steps means whatever steps we have defined here, we can save the results at those steps as well. Okay, so this was about the construction stage tab, how we can create the construction stages. Now let's quickly define the construction stages for our bridge. So I'll just delete these additional steps which we have created. Now so for this CS0 I have to add first I have to add CS0 structure group. So here, so one more thing before adding these structure groups, I have created time dependent effects here as well. So let me just show you. So here I have defined the time dependent material properties as well. So material properties which I have used for my structure is C4050 I have used for substructure and for slab, and C5060 I have used for my girder. Okay, so for that I have created the time dependent material properties as well. So I have considered time dependent effects only in my superstructure. So if you want, you can consider for substructure as well. So for that, if you see the definition, this is the definition. I have considered the FCK is 50 MPa, relative humidity 70, and notional size for now I have defined as 1 meter or 1000 mm. So as you know, this notional size is dependent on the sectional area and perimeter. So it is a function of section. So once we have defined all the sections, it can be updated as per the section dimensions. We will see how we can do that. Okay. So here then type of cement we have selected class N, and here Euro type of code we have selected EN 1992 bridge code. Okay, then age of concrete at the beginning of shrinkage we have considered as 3 days. Then now if we click on show result, so it will show us the graph of creep coefficient with respect to time that we saw in the presentation as well. Similarly, so here we can see from age 13 to 10,000 this graph is there. Suppose if your construction stage duration is more than 10,000 days, in that case the program will automatically extrapolate the values from this graph. Okay. Similarly, then we have the shrinkage strain which is given similar to the one we saw in the presentation. Okay, so I'll close this. Then similarly we have defined for compressive strength as well. So here we have to go for FCM, which is FCK plus delta F, which is the standard deviation. So FCK is 50 MPa and standard deviation is 8 MPa. So FCK plus delta F will be 58, and based on that the graph is plotted here. Okay, so that was about the time dependent material properties that we have defined. Then I was talking about the notional size, which we have given as 1 meter, but it will depend on the section. So for that, what we can do here, we have a option to update, change a parameter. Sorry, not here, we have to go to properties. Here we have option of change property. So here we can update the notional size based on the section dimensions. Okay, so here we will select all my superstructure elements. So here I will go for select option and select all the superstructure elements, and then I'll just apply. So the properties will be updated. So for our example, I have already done that. So you can see the notional size is updated based on the section properties. Okay, so yeah, I'll close this. Then we will have, yeah, so now we will define the construction stage analysis. So for CS0, my substructure will be activated, and the age at which it will be activated is 28 days. Then boundary that I want to activate is sub, and load I want to activate is self-weight. So whenever a load is activated, we don't need to activate it again. So this self-weight, as I have activated, so whatever elements are activated in the later construction stages, self-weight will be activated for them automatically. Okay, so this is the definition for self-weight, sorry, for CS0. I'll press apply. Then we'll go to CS1. So here now CS1 element I want to activate, which is the span 1. So this also I will activate at 28 days. So we are going for full staging. That means the deck will be cast in C2. So when the formwork will be removed, that will be at 28 days, when the girder has achieved the concrete has achieved its strength. So that's when I will activate those superstructure in the program as well. So that's for that I will add at 28 days. Then boundary BG1 I will activate here, and load, here we have to activate a pre-stressing load for span 1. Okay, so I will add PS11 to PS14. For that I need additional step. So I will add few additional steps. Okay, so duration will not make that much difference here. The reason why I am adding these 4 steps is because I want the different point of activation for all these 4 tendons. The reason for this is I want to capture the effect of sequential pre-stressing. Okay, now I will add this at 0.02, this at 0.04, 0.06 and 0.08. Okay, so now all these 4 loads are added. So I'll press apply. So here I am getting an error. So yeah, so here I have forgot to define the duration. So here I will give a duration of 14 days. Okay, now I will go for CS2. So here also I will give a duration of 14 days. Then I will add CS2. So this also will be of 28 days. Then boundary BG2 I will act, and all these I'm activating at deformed location. So 0.02, 04, 06, 0.08. Okay, these 4 steps we have added. So this I will activate at 0.02, 04, 06, 08. Okay, so CS2 is also defined. Similarly, I will add CS3. So duration for this I will keep it as 14 days. Okay, so element that I want to add is CS3. Age will be 28 days. Okay, then boundary BG3 and load will be 02, 08. One. Okay, so now these 4, so this is also done. Now I will just apply. So all the 4 stages are defined. Now is the time for this is the long term stage. So here duration will be 10,000 days. So this comes out to be around 30 years. So this we are defining to capture the long term effects of creep and shrinkage and see if our structure is safe after the 30 years. Okay, now here only one load I have to activate, which is the SI deal, and that I will activate at day 1 of this stage. Okay, then I'll press OK. Okay, so all the loads have been activated here. So now I'll close this. So now if we see the construction sequence, so CS0 only my substructure is activated. In CS1 my span 1 is activated with pre-stressing. In stage 2 my second span is activated with pre-stressing. In stage 3 third span is activated with its pre-stressing, and stage 4 is the long-term stage for SIDL load. Okay, so you can see all the loads are also reflected here, which have been activated. So here I have this temperature rise and fall cases as well, and those are activated post CS, so that's why they are not shown in construction stages. Okay, so now we have defined the construction stage for our analysis. Now we can also customize our analysis as per our requirement in the construction stage analysis control tab. So for that we'll go to analysis. Here we have an option of construction stage analysis. Here now this is our control tab. So here I can, first option is to run the analysis either till last stage or any other stage. So suppose I want to run analysis only till stage 2, so I can select here other and run till stage 2. However, now I'll go for last stage. Then we have an option of analysis option of linear analysis, non-linear, or material non-linear analysis. So suppose I want to go for material non-linear, so I can select material non-linear, and here I can customize the material non-linear analysis with the number of iteration, number of load steps, and the convergence criteria. Okay, for now I'll go for linear. Then here we have independent or accumulative. So independent means each and every stage of a construction stage analysis will be treated as a independent stage. So the results from previous stage will not affect that particular stage. However, in accumulative stage, whatever results we are getting from the previous stage, the stress condition, the results will be carry forward to the next stage. So that will act as an initial condition for the next stage, and based on that the current stage analysis will be done. However, in independent this does not happen. All the stages are treated as independent and separate, and the analysis is performed without any influence from the earlier stages. Now coming to the P delta effect. So if I want to include the second order effects, so I can check on this P delta effect option. Here I can give the control for P delta as well if I want to. Now if I want to include the time dependent effects for our bridge, so I can check on this option, and here this is my time dependent effect control tab. So I can either select creep shrinkage, or I can select both creep shrinkage, or if I want to select only creep or only shrinkage, we can select these options. So in case of creep, what happens, the whole so suppose you have defined whole construction stages of total age of 20,000 days. So what the program does is it divides that construction stage into number of time steps, and the creep stress will be calculated at those time steps. So how those time steps are generated, that is shown here. So suppose your total construction stage duration is of around 10 days. So in that case the steps will be created, number of steps will be created as 2. So if it is 1000 days, then it will 7 steps will be created, and if it is 10,000 days, 20 steps will be created, and like that. So if you want to increase the number of steps, we can increase that. So with that the accuracy will increase. However, the computational time will also increase with increasing the number of steps. Okay, then variation of compressive strength, if you want to consider that or not, we can check on or check off this option. Then we have tendon tension loss effect. Do we want to change with variation of tendon force, or we want to keep it constant? We can select the option here. Now once the time dependent effects are done, we'll press that OK. Now here we have an option of load case to be distinguished from dead load for construction stage analysis. Now when we perform the construction stage analysis in MIDAS 7, what the program does, any load apart from tendon pre-stress, tendon primary, tendon secondary, creep and shrinkage, all the loads apart from these loads will be clubbed to dead load, and the results of those loads will be shown in dead load. But there might be instances when we want to see the results of certain loads separately, because the factor of safety for those loads is different from that of dead load. So for that we have to distinguish them from the dead load. So for that we have this option. So here if I press add, so here I can distinguish, suppose I want to distinguish the SIDL load, wearing course as well as crash barrier, as this factor of safety is different from the self weight. So here I will give as SIDL wearing course, and here I will select SIDL wearing course and I'll press OK. So here SIDL wearing course will be separated from dead load. Similarly I will separate SIDL crash barrier as well. So here this will also be distinguished from the self weight. Now we can see the results for these two cases separately in construction stage analysis. Okay, then we have cable pretension control, if it is external or internal force. So these factors are mostly used for cable state bridges. Then we have initial displacement for construction stages. So if we want to include the initial tangent displacement for our structure, then we need to check on this option. So basically whatever deformation that we see in post CS are the net deformation, that means the deformation of that particular node. It does not include the effect of initial tangent due to the activation of earlier element. However, in reality, if we are activating, the deformation of earlier element will influence the deformation of the next element. So for that, if you want to see that effect, for that we have to check on this option of initial tangent displacement for erected structures. Then if I want to do that, I'll check on this option. Then we have an option of beam section property. Do I want to keep it constant or do I want to change it with tendons? So if you are activating tendons, so based on that there will be a hole in section, and as well as the tendon material properties and section properties will be used to calculate the effective section properties. Okay, then if I want to calculate the concurrent forces in frame, then I need to check on this option. And if we have composite section, then we can get stresses and forces for part sections as well. So if I want to do that, I'll check on this option, and here we will get self-constrained forces and stresses as well. Okay, and then if I want to save the output for current stage, then I can check on this option. More details on this are also available in online help manual, so I would recommend you to go and read that as well, so you will get more in-depth detail about the construction stage analysis control. Okay, now I'll press OK for this. Now we are in CS4, so we cannot add modify this because we are in CS4. To make any changes to a structure or add anything, we need to be in base stage. So I'll just close this. I'll be in base stage. Now I will open construction stage analysis control, linear time dependent effects. Okay, then I will add quickly. I'll add this will be SIDL WC, SIDL CB. Okay, then I want initial tangent displacement. Okay, now my construction stage analysis control is also created. Now I can run the analysis now, and then we can see the results for our analysis. Now the analysis is complete for our bridge. Now let's look at the results for our analysis that we have done. So first let's go to CS0 and let's look at the bending moment diagram due to self weight. So here I will select beam diagram MY, and for dead load, let's see. So now here you can see the bending moment diagram in pier. Then if CS1, my span 1 is activated, so this is the bending moment diagram. This is the cantilever part due to which I'm getting a small hugging moment here, and this is the sagging moment. Then coming to CS2, similar, CS3. So, and then the long term will be CS4. Let's see the magnitude what I am getting here. So I'll just make it fixed. So let's make it kilonewton meter. So the moment is around 20,867 kilonewton meter, and similarly hogging moment is 19,468 kilonewton meter. So this is the bending moment. Similarly, if I see for tendon primary, okay, so this is for tendon primary. If we want to see for tendon secondary, that means the secondary effect. So here also we are getting the secondary tendon moment. Then let's see the creep secondary. So we are getting a creep secondary of 124 kilonewton meter supposed at the end of construction stages. So CS4 is the long-term stage, so here we are getting creep secondary of 753 kilonewton meter and minus 784 kilonewton meter. Okay, so this is for creep secondary. Similarly, if you want to see for shrinkage secondary, so that's less because our structure is released at the ends. Then let's see for summation how much we are getting. CS summation means a summation for everything. Then if I want to see for SIDL, so we have distinguished this from dead load, so that's why we can see their result independently. This is for bearing cores, and then we have for crash barrier as well, so that comes out to be this much. Okay, so these are the results in the construction stages. If I want to see the deformation of my structure, so let's see the deformations as well. So let's go to CS1. Okay, deform. So this was not activated for dead load. So these are deformations. Let's see in mm. Okay, CS2. So now I need to, so you can see a jag, like kink here. So this is the net displacement that is shown here, but we need to see the real displacement that is happening. For that, we first checked on the option in construction stage analysis control for tangential displacement. Similarly, I need to check on the stage step real displacement, and then I'll press apply. So this is the real deformation that is happening. So we are getting a deformation of 10 mm here at the center, I guess. Okay, and then CS3. So this is a deformation due to dead load. Now let's see for summation how much we are getting. So for summation we are also getting a hogging deformation of 10 mm. Okay, like this we can see the results for our members for all the load cases: dead load, tendon primary, secondary, creep, shrinkage. Okay, now I want to see the results for pre-stressing. So for that I'll go to results. Here we'll go to tendon. Here in tendon we go to tendon loss. Okay, so here we can see the result of I'll just make it kilonewton meter, or let's make it Newton mm, so it will be an MPa. Okay, so this is the tendon stress. So this is tendon stress after immediate losses. Okay, for tendon AL1. So here I can select any other tendon as well. So whatever tendons we have defined will be shown here. And then here I can select the stage. What are the stresses in that particular stage? What are the losses that are happening? So here you will get elastic losses, creep, shrinkage, relaxation loss, or stress after all losses divided by stress after immediate loss. Okay, so this you can see. Okay, similar thing can be seen in tendon loss graph as well. So here in CS1, this is the tendon loss, tendon stress along the length, the span of the bridge. Then CS2, there is a little bit loss that is happening. Then we have CS3 and then CS4. Okay, so here you can see how the stress is varying with the construction stages. Okay, so this is for real one. Similarly, I can see for all the tendons. Okay, so this either we can view in the tabular format or we can view in the graphical format as well. So these were the stresses. Similarly, we can see the stresses for our section as well. So here we'll go to beam stress diagram. Then we can just see how the stresses are varying for our section. Okay, so let's go for undeformed. Okay, how the stresses are varying. So here I can see at all the 4 points 1, 2, 3, 4. Okay, so yeah, this was, so we can see forces, stresses, deformations, tendon results and whatnot. So suppose we have composite section, then we can see results for composite section for construction stages. Here we can see part-wise stresses for slab as well as for girder, and we can see self-constrained forces and stresses as well. Okay, so these are for composite sections. So yeah, this is all about the construction stage analysis in MIDAS Civil. Now let's have a quick question answer sessions where I'll try to answer most of your questions. Yeah, so that's all from my end regarding the presentation on importance of construction stage analysis. Now let's have a quick question answer session where I will answer all your questions based on the topic of construction stage analysis. So yeah, thank you all for being part of this session on construction stage analysis and its importance. Thank you for taking out time from your busy schedule. We appreciate it. In case of any further queries, kindly write us write us on globalsupport.midasuser.com. So here you can raise your query and we will try to answer it in less than 24 hours. So yeah, thank you for your time and hope we will meet in such sessions in future as well. Thank you.